and d is the distance between the openings. D is not the size of the opening. That could be important at times. D is how far apart they are. Okay. So before I get to the three examples that I asked you to complete, let's talk about the fact that you have the lambda equals xd over nl formula, which is not always valid. If you're given a question, and I'm going to actually go to, yeah, sure. Let's go right to example 1 here. So what I had told you is after reading this question, we could decide that d is the distance between the two openings, which is 0.3 millimeters, and I converted that to meters. We're talking about, for the first question in this, the bright fringe at n equals 1, so that's the first bright fringe away from the center. It's detected at a particular angle. When you do this question, you don't have to worry about which formula you're going to use because you're going to use the angle, right? So you get the opportunity in this example to use this formula, and it's always valid. By the way, since the angle is less than 10 degrees, this is the formula that we're going to use, but you could use the other formula if you wanted to, but it would be a lot of work. So we put in d times sine of 0.08 over 1, and this is the answer that I get. I get 4.2 times 10 to the negative 7 meters, or about 420 nanometers. You're then asked at what angle would we see the n equals 2 at? Well, for the n equals 2, you would just use your formula lambda equals d sine theta over n, but you would put in the wavelength you found along with d, but you would use n equals 2. You cross multiply there, you're going to take the 4.2 times 10 to the negative 7. You're going to multiply it by the 2. You're going to divide it by the 0.0003 and then go inverse sine. And when you do that, apparently you get 0.16 degrees. And when you do that for n equals 3, you get 0.24 degrees. So are we okay with that example? Okay. So now, if we take a look at the next example, number 2, again, yesterday what I did was I went through the question with you, and I indicated to you that it says the student measures the wavelengths of light emitted by some sample. The light passes through two slits that are separated by this distance of 0.26 millimeters. Well, that's the distance between the slits. That's d in the formulas. It says the distance between the second bright fringe, so that's telling us n equals 2, and the central antinode, which is the middle, that distance from the middle to that second bright fringe is 1.18 centimeters, so that's x. L, of course, is this distance this way, which is 3 meters. Now, the question is theta less than 10 degrees? Because this is setting you up for success or failure based on whether it's less than 10 degrees. Because you have a formula, lambda equals xd over nl, it's right here. But if this angle is not less than 10 degrees, then you will get a wrong answer. So how do we do that? We determine if the angle is less than 10 degrees by just doing a trigonometry problem. You know, there's your diagram. Your double slit, I didn't put it in here, but your double slit is over here. Your screen is over here. The bright spot is here. That's the n equals 2. So you simply do a trigonometry problem. And can you confirm that when you find that angle, it's 0.225 degrees? So the angle is less than 10 degrees, and that means you can go ahead and use this lambda equals xd over nl, and you get 5.1 times 10 to the negative 7. Can I get everybody to just confirm with that calculation that that's what you get? So you get 510 nanometers. Are we okay with that? But I want to show you something here that I think is kind of an important idea. You go through that process and you get this angle, inverse tan of 1.18 multiplied by 10 to the negative 2 divided by 3. And I was doing something in the first period this morning in trig with math 30, and I was in the wrong mode there. And you get this angle, right? Okay. I'm just going to store that angle so I can retrieve it in a minute. But once you see that angle's less than 10 degrees, you go ahead and use the shabby, what I call the shabby formula. The formula that doesn't always work, but it's good enough this time. Okay? Multiplied by 0.26 times 10 to the negative 3 divided by 6. 2 times 3 is 6. Okay? And this is the answer I get. Okay? And I've used a formula that's not correct formula. But would you agree that this angle of 0.225 degrees is significantly less than 10 degrees? Like, and what we would actually write here is this. Like, it's really less than 10 degrees. Let's look at what happens if I use the other formula, lambda equals d sine theta over n. Well, d is 0.26 times 10 to the negative 3 times the sine of that angle that I stored divided by n, which is 2. Look at the answer I get. It's very, very close to the answer that the shabby formula gave me. Would you agree? And certainly to 2 or 3 digits, it's going to be the same. Are you with me? There are some students who will say, if you're going to make me go through the trouble of finding that angle, why don't I just use the other formula anyway, regardless of the result? And the answer I would say to you is go ahead and do that. But if the angle were 9 degrees, or even 5 probably, you might get an answer with the good formula that's not in the multiple choices. Because Alberta Ed follows the rule that says if it's less than 10 degrees, they're going to calculate an answer using the shabby formula. So you need to be aware that sometimes you might use the proper formula and get an answer that differs slightly from the multiple choice. If it's numerical response and it's less than 10 degrees, they'll accept either answer. Okay? So it could be that at a bigger angle you get 5.1 times 10 to the negative 7 with the shabby formula, and you get 5.0 times 10 to the negative 7 for the good formula. All right, and I also asked you to complete number 5. We have 2 microwave generators, and they are put 15 centimeters apart. That means that's D. This is not a case of you having one big sweeping wave of microwaves hitting 2 openings. You have an opening here that the microwaves are leaving. You have an opening here that the microwaves are leaving. And as the microwaves leave either of those openings, they spread out, producing that interference pattern. So this is D. L is 70 centimeters. X is 23.8 centimeters. So I did a math 10 problem here where I find this angle by using tangent of that angle is equal to opposite over adjacent. And when I find that angle, I get 18.77 degrees. So that's definitely more than 10 degrees, which means to answer this question, you have to use this formula. And when you put the numbers in, I believe you get 0.024 meters. Can you confirm that? Okay. What would have happened if you didn't do that check here? Well, somebody might have looked at this question and said, well, here's X, here's D, here's L, and N is 2. And if you use lambda equals XD over NL, you'll get a significantly different answer than the 2.4 centimeters. XD, 23.8, 0.238 times D, which is 0.15, I have to use meters here, divided by N times L. I mean, I could go divided by 2, divided by 0.7, but 2 times 0.7 is 1.4. So I'm just going to divide by 1.4. And I get that. Which, you know, we're not splitting the atom or landing people on Mars with this. You're only off by a tenth of a centimeter, but on an exam it would be marked wrong. If it were numerical response and it said, what is it to the nearest centimeter, and you put 2.6 and it's actually 2.4, you're wrong. So before we do the graphical question here, does anybody have any questions? Well, and this isn't just a made-up response. As I said yesterday, we used to do this experiment. And we would walk across the room with a microwave detector, and it would go to a maximum, and then it would decrease, 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 decrease. You could still see a reading on the needle, and it also had a speaker that would squawk, a continual squawking noise when microwaves were hitting it. And when that detector was in just a particular place, it had to be very precise, it was almost silent. So there was almost no microwaves there. You're asking, why does it gradually decrease to nothing as opposed to looking at the laser light? And the only explanation I can come up with is that, well, I have a couple of ideas. One, this isn't a very specific wavelength. It's maybe a range of wavelengths. And if you look at where the energy distribution would be, if it were one specific wavelength, and then you start adding on top of that the energy distributions for other wavelengths, kind of an error in the wavelength, you're going to get that gradual decrease to nothing. I think it also might have something to do with the fact that it's not perfect diffraction. I mean, I can go back here. I don't want us to get lost in this diagram I'm going to show you. I really don't want us to get lost in this diagram that we looked at yesterday, because I think it can mislead you and make things more confusing in terms of what you need to know. Okay? But in order for us to get this nice distribution of energy, we're assuming it's a perfect kind of circular diffraction of the wave as it goes through each opening. And I just don't think it's a perfect diffraction when those microwaves leave those two generators. In other words, I think there's a lot of error there. But I don't have a definitive answer for your question. I don't. I'm going to leave it there. Light seems to be special. If you do it with sound waves, even though you have a very specific frequency or wavelength of sound waves, you do get that wavy distribution of energy. When you do it with microwaves, you get that same wavy distribution of energy. But if you do it with a laser, you don't. Other questions? Yeah.
Do the two equations work for any kind of wave?
Yes. They work for any kind of electromagnetic wave, meaning visible light, ultraviolet, infrared, radio, gamma, X-ray, etc. And they also work for any kind of wave, mechanical or electromagnetic. So they work for water waves. They work for sound waves, which are not electromagnetic. Some people want to put sound on the electromagnetic spectrum. They work for jello waves. They work for any kind of waves at all. Yeah. Other questions?
Which formula do we use on our Ritchie response? How do we know which one to use?
You find the angle, and if it's less than 10 degrees, you can use either formula. If the angle is more than 10 degrees, you have to use the formula with the sine of theta in it. I mean, I guess we have a few more minutes here before I finish this off today. I can explain to you why one formula is valid and the other one isn't. Okay. Let me go to this diagram here. Yeah. So if we dissect this crappy formula, I can write this as d over n multiplied by x over L. And don't worry just for now why I've decided to do that. But would you agree that lambda equals xd over nl is the same as me writing that? Okay. And on the other hand, we have this good formula, which is lambda equals d over n times sine of theta. Now, sine of theta, if you look at this triangle, sine of theta is in a triangle opposite over hypotenuse. This is the hypotenuse. And the fact of the matter is the geometry of those concentric circles gives us this formula, lambda equals d sine theta over n. It works. Okay, it's valid. When you look at x over L, x is opposite, but L is not the hypotenuse. L is the adjacent side. So this, take a gamble. Nope, shouldn't have done that. That, x over L, is not sine of theta. That is tangent of theta. Isn't it? It's opposite over adjacent. So what this formula that is not a great formula is d tan theta over n. What the real formula should be is lambda equals d sine theta over n. I mean, you don't have to be a genius to understand that these are two different expressions, right? Sine of theta is not equal to tan of theta. But at small angles, it's close. Because, I mean, look at it. There's a number of ways to look at this. If this angle is very small, what can you tell me about the length of the adjacent side as opposed to the length of the hypotenuse? Well, at small angles, they're going to be very, very close to being the same thing. Which means at small angles, tangent of theta and sine of theta are pretty close. In fact, if I put into my calculator for y1, tan of theta, and for y2, sine of theta, and I go to my mode, make sure I'm in degrees, I go to my window settings, my table settings, and I start at 0 degrees and I go up by 0.05 degrees, 5/100ths of a degree, 1/20th of a degree, and put it on automatic and go to my table. This is tan of theta. This number is sine of theta. They're very, very close to each other, really close to each other. Even down at 0.35 degrees, look at the difference between these. Very, very slight. But if I go into my table setting, I'll go to ask now, and I put in, 1 degree. Well, at 1 degree, they're pretty close, aren't they? 2, 3, 4. what you discover is as the angle gets bigger, the hypotenuse is bigger compared to the adjacent side, so the tangent starts getting larger compared to the sine. I can continue to do this 5, 6, 7, 8, 9. Somebody somewhere has decided, for Alberta Ed, that 10 degrees is the cutoff mark. They've decided that we'll go with 10 degrees because if it's less than 10, these numbers are close enough that we really don't care. The question then becomes, and many of you will already be fasted in your head, why do we use the crappy formula? And the answer is, seriously, it's easier to measure L in the lab than it is to measure H. When I'm holding a laser, and you're going to be doing a lab on this either tomorrow or the next day, when I'm holding a laser, you're not going to be doing it against the ceiling, you'll be doing it against the wall. And I do this, and I want to, this is going to be very difficult for me to do, but you see the dot that's immediately to your left, it's right there. This is the dot I'm talking about, of the center point. It's easier for me to measure the straight line distance from this point here up to the ceiling than it is to measure this straight line distance from here at an angle over to that dot. My question was always as a physics student, well, yeah, okay, I'll measure L, but why don't I just calculate the angle and use the good formula? And I was always told because the other formula is good enough for small angles. And I don't like that. I mean, science should be as precise as possible. I think the 10 degree cutoff point is basically that if you round to 2 or 3 significant figures, you're not going to see a difference. Okay. One final point here, and I'm just trying to draw a connection between physics and math. I'm going to graph y equals sine of theta. I'm going to graph y equals sine of theta up to 90 degrees. So this is, in you math 30 people, you know that this curve goes up, and then at 90 degrees it starts going down, and then it continues its cycle, right? I'm going to draw now or graph on here tangent of theta, and you should know that it starts at the origin and it curves up against an asymptote. This is if you're in math 30, against an asymptote at 90. So when I go graph, here's tangent. And it's this range in here. I'm not using range as in domain and range. I'm just saying this region. It's this region in here where, I mean, you can't really see the difference. I mean, sine is doing this. Sine is doing this. Tangent is doing this. But they're against each other there. All right, let's move on. I want to do now the final example here. It's a graphical analysis question. This is for number 3 and 4. So let's walk through this together. In a double slit experiment, different colors of light are used to produce different interference patterns using 2 slits that are etched on a glass slide. So this is old school. We'll talk tomorrow about what these things are that I've been using. This is not a piece of glass that I've etched 2 lines in. It's called a diffraction grating, which is something different. So they use different colors of light, which have different wavelengths. And by the way, when you do your lab, you will know the wavelength. You'll be able to look at this, and my eyes can't read that, but you'll be able to read what the wavelength of this red laser light is. So when you collect your data for the red, you'll know lambda. They project the images, the diffraction and interference patterns, on a screen 1.5 meters away. That means L is 1.5 meters. And what they do is they measure the distance to the first order antinode. They measure X for n equals 1. Your lab will be more involved than that. I will want more data, and we'll get to that later. The results of the experiment are shown below. So they graph. They graph the wavelength here, and they were lucky enough to have 1, 2, 3, 4, 5, 6, 7 different colors. They probably didn't have 7 lasers. They probably used white light and different colored filters. So a red filter allows only a particular wavelength of red light through. A green filter, only a particular color of green light. And this is the wavelength. This, of course, is the manipulated variable. Hey, Charlie Brown, what color should we use next? Well, let's use the red. So they decide on which color to use. And then, do me a favor, Peppermint Patty, measure that distance while I'm holding the red light against the diffraction grating or the double slit. So this is the responding variable. Now you want to be a little bit careful here because the responding variable is the distance to the bright line, which is the variable x in the equation. But x in this graph is lambda. You get my drift here? Okay. The question is, what's the slope of the line of best fit? And then more importantly, what's the distance between the slits? So what this problem is about is how do we use this graph to find D? That's the problem. You're going to have a different problem, and your lab will not be a graphical analysis, okay? Well, what we need to do is compare, and the number of graphical analyses we look at from here on in is going to start climbing. We have to keep reviewing this. We have to compare the math equation of the graph and the physical equation. In case it's not clear, physical means physics. So what is the math equation? Well, the math equation is y equals slope times x plus b. What is the physical equation? Well, the physical equation, which I'm not going to write down here, I'm going to put it over down here in this bubble. The physical equation is lambda equals xd over nl. By the way, not that you really need to here, but what are some of these distances? Even the biggest distance is about 17 centimeters. Would you agree? What is L? 1.5 meters, was it? So if you have 1.5 meters, which is 150 centimeters, and the biggest x is 15 centimeters, will this angle be less than 10 degrees? Well, I think it will be. We can do a quick calculation to confirm it, but it's going to be. You can go inverse tan of 15 divided by 150, and let me know what you get, Annalie. 5.7. So this is why we're able to use this formula. And by the way, I don't want to go too deep into this, but if the angles were too big, this would not be a straight line. It would be curvy. So this is the physical equation. We want to rearrange this equation for y that's plotted on the graph. So take a look at your graph. What variable from that equation is plotted on the vertical axis? It's x, isn't it? So we have to rearrange this equation for x. Well, if I cross multiply, I get nl lambda equals xd, which means x equals n times L times lambda over D. Capiche? Okay. So I'm going to rewrite this one more time as x equals lambda n L over D, and then I'm going to rewrite it one more time up here. I'm going to write it as x equals NL over D times lambda. Somebody enlighten us as to why I decided to write it that way. Annalie? Right. Right. Lambda's on the x-axis. I'm doing a comparison. So if and this is again tricky because this x right here that I'm going to highlight, this x is not the horizontal variable. It's the distance between the bright n equals 2 image and the central maximum. It's what's plotted on the vertical axis. So that's why. And as Annalise said, the reason why I kind of pulled that lambda out to the side is I want to have a comparison here that's a one-to-one comparison of everything. Now, by the way, according to the physics equation, this should be plus 0, shouldn't it? Because there's no other thing in the equation. So if there is some y-intercept, we don't need to worry about it. It's just there because of experimental error or something. It's not part of the physics. But what this means ultimately is that the slope of the line is equal to this. That's the tough part. Now the mechanics of this is that you have to find the slope of that line and set it equal to NL over D and solve for D. So how are we going to find the slope? I've kind of suggested to you in the past that I think the best way to find the slope is to do a linear regression. You don't have to. You could pick this point, and I'm going to have to do some estimating. This point, and draw a triangle on the graph and calculate your rise and your run. But there's a more efficient way to do that. And that's to go to stat edit and enter in those two data points. Now I have some data in here already, so I'm going to get rid of it by going to my memory management menu and clearing all lists. Stat edit. And a y-coordinate of 9 times 10 to the negative 2 meters. So I'm going to put those numbers in. 4 multiplied by 10 to the negative 7. And then the y-coordinate of that point is 9 multiplied by 10 to the negative 2. And now I'm going to take a look at the second point. Now, you know, if you want to choose a different point, feel free. I'm choosing this red point up here that I'm pointing at. The x-coordinate there is, well, we have a bit of an awkward scale here. This is 4.4. This is 4.8. This is 5.2. This is 5.6. Each of those squares is 0.4. So this is 6.4, 6.8, 7.2 is here, 7.6 is here. I mean, I might say halfway between would be 7.4. I would say 7.5. And whether you do this on paper or with a linear regression, you still are going to have to use that skill of reading that data point as accurately as you can. So the x-coordinate for that point is 7.5 times 10 to the negative 7. The y-coordinate is 16, 17, 18 times 10 to the negative 2. Just before you commit yourself to finding the linear regression, double check to make sure you've entered the data correctly, and I think it's fine. So now we don't care about looking at the graph here. We don't care about drawing the graph or plotting the data. We just want to find the slope. So you go Stat, Calc, choose Linear Regression. Now I have R squared and R on there. We've talked about that before, I think. Don't worry about it. My slope is 257,143. So for number 3, 3 said, what is the slope? For number 3, it's 2.6 times 10 to the 5. And by the way, there would be no units on that slope because the rise was measured in meters and the run is measured in meters. So when you divide meters by meters, that's what you get. You just get the number. You don't get units. Now for number 4, we've already done the hard work, the heavy lifting. The slope is equal to NL over D. That was what came out of our thought analysis comparing the math and the physics. So I can put in all of the information. I can put in 2.6 times 10 to the 5 for the slope. I'm going to put 1 for N because all of their data was to the first order antinode. L was, I've forgotten again, was it 1.5? 1.5. And then we want to find D. So you're going to cross multiply here and get 2.6 times 10 to the 5 times D equals 1.5. So D will be 1.5 divided by the 2.6 times 10 to the 5. You know, if you want to use all of your decimals, you could type it in. You could go 1.5 divided by 257,143 would be good enough. So you get 5.8 times 10 to the negative 6 meters. And by the way, you know, how we enter these, this was 2.6 times 10 to the 5. So you would enter 265. We got here 5.8 times 10 to the negative 6. So you would enter 586. I'm not sure what I did in our Google Classroom when I posted these answers. Interesting. I guess the answers that I posted in Google Classroom were wrong. I think I know why that is. Let me just check something. I think they're wrong because I didn't actually do the work yesterday. I went to a recording of a previous year with this lesson, and the graph might have been different. And I just looked at the answers. Things. I think this is the most important aspect of this question, is doing a comparison of the physical to the mathematical equations. So what you're working on today are all of the attached questions, 1 to 8, I believe it is, on page 33 of the handout. Tomorrow, between tomorrow and the next day, I want to try to finish it all up tomorrow, but I think finishing up this section and doing lab work tomorrow is too much. So what we're going to do is we're going to do the next lesson tomorrow, which deals with a continuation of this idea that we've been talking about. And then on Thursday, you're going to have a lab, and then Friday we'll move on. And I'm going to have to shave off some time maybe in the next unit. We still have lots of time, but I want to make sure that we keep that lots of time for review for the diploma exam. So get to work on that, please, and I will come around and I will help you out.